Hi, my name is Neil Vore, and I'm an 8th grade student at Cuesta Elementary School in Mountain House, California. I joined the YRI Fellowship program because I'm passionate about learning, research, and sharing ideas that can make a positive impact. One of my biggest goals is to publish my own research paper and develop skills in critical thinking, problem solving, and academic writing. The fellowship gave me an opportunity to work with mentors, explore real-world topics, and improve my ability to communicate ideas clearly and confidently. I believe this experience will help me grow both as a student and as a future leader, while allowing me to contribute meaningful work through my research and publications. Good morning, everyone. Before I begin, I'd like to ask you a quick question. Have you ever noticed that when someone is extremely tired, stressed, or even sick, the way they speak changes? Maybe they pause more often, struggle to remember words, or use simpler language. Now, imagine if those tiny changes weren't caused by being tired, but instead were some of the earliest warning signs of a neurological disease. My name is Neil Vore, and through the YRI Fellowship, I had the opportunity to investigate exactly that question. Over the past several months, I've been researching how AI can analyze speech patterns to detect early signs of Alzheimer's before noticeable symptoms appear. Today, I'd like to take you through that journey, from the med problem to the AI model I developed to the results and why this research should someday improve healthcare. Now, why does early detection matter? Let me ask another question. If you could detect Alzheimer's 5 or even 10 years earlier than we do today, how might that change someone's life? Earlier diagnosis could allow patients to receive treatment sooner, participate in clinical trials, prepare with their families, and potentially slow disease progression. Unfortunately, that's not how our healthcare system currently works. Today, more than 55 million people worldwide are living with dementia, and Alzheimer's accounts for nearly two-thirds of those cases. As you can see from this timeline, cognitive decline begins long before symptoms become oblivious. Then, neurological disease hits. First, tiny neurological changes occur. Then, language begins to change. Eventually, memory problems become noticeable. Only after that do most patients receive a diagnosis. By that point, significant brain damage has often already occurred. That is the gap I wanted to address today. Now you might be wondering, why focus on speech? The answer is actually fascinating. Speaking is something we do every day without thinking about it, but inside our brain, it's incredibly complicated. Every sentence requires memory to recall information, attention to stay focused, executive function to organize thoughts, word retrieval to choose the correct vocabulary, and semantic processing to ensure everything makes sense. When these systems begin to worsen, speech often changes before other symptoms become obvious. Someone may begin searching for words, using vague descriptions, or speaking with longer pauses. Because speech naturally reflects so many brain functions, I believed it could become a powerful window into cognitive health. So that brings me to my main research question. Can AI identify cognitive decline simply by analyzing language? To answer that question, I established four research objectives. First, I identified measurable linguistic biomarkers. Second, I compared speech from healthy individuals and those of Alzheimer's. Third, I trained a machine learning model capable of recognizing these patterns. And finally, I evaluated whether the model could achieve clinically meaningful accuracy. In other words, could language itself become a digital biomarker for brain health? Now here, I used the Dementia Bank Pit Corpus dataset. I analyzed 544 speech transcripts, and out of them, I found that 303 people had healthy speeches, and 241 had speeches relating to Alzheimer's disease. The reason being, every participant completed the same task, known as the cookie theft picture description task. Participants were shown an illustration and asked to describe everything they observed in the image. This standardized task is extremely important because it controls for topic variation. If participants were discussing different subjects, it would be difficult to determine whether language differences were caused by cognitive decline or simply different conversation topics. And this creates a highly controlled dataset that is ideal for machine learning analysis. Now, once the transcripts were collected, the next challenge was transforming human language into numerical data that a machine learning model could understand. To accomplish this, I extracted features from three major linguistic dimensions. The first category was lexical features. They measure vocabulary richness and diversity. Examples include type token ratio and Brunet's index, which helps quantify how varied a person's vocabulary is. The second category was syntactic features. These evaluate sentence structure, grammatical complexity, and relationships between different types of words. Measures such as pronoun-to-noun ratios and syntactic depth can reveal changes in language organization. And the last category was semantic features. They focus on meaning and content quality. Semantic measures evaluate how specific, detailed, and information-rich a person's speech is. Together, these features create a multi-dimensional representation of language that captures both vocabulary use and communication effectiveness. Now, one of the most innovative aspects of this project was the development of the Vague Language Index, or VLI. The VLI was designed to quantify linguistic imprecision, which is a common characteristic of cognitive decline. For example, a healthy speaker might say, "The boy is stealing cookies from the jar." This sentence contains clear subjects, actions, and objects. In contrast, a person experiencing cognitive difficulties may say, "The kid is getting that thing." The specific details have been replaced by more generic and less informative language. To capture this phenomenon, the VLI measures several factors, including imprecise pronouns, generic nouns such as thing or stuff, and hesitation markers such as or. By assigning numerical values to these patterns, the VLI transforms a subjective observation into a measurable feature that can be used by machine learning algorithms. This index ultimately becomes one of the strongest predictors in the entire study. After feature extraction was completed, I trained a random forest classifier to distinguish between healthy individuals and Alzheimer's patients. The process begins with a speech transcript. Linguistic features are extracted and then filtered through feature selection techniques to identify the most informative variables. These selected features are then used to train the random forest model, which generates a prediction based on the patterns learned from the previous examples. Random forest was chosen for several reasons. The first, it performs exceptionally well in complex datasets containing many interacting variables. Second, it is resistant to overfitting, meaning it generalizes well to new data. Third, it provides interpretable results by revealing which features contribute most strongly to predictions. These advantages make random forests particularly well suited for healthcare and diagnostic applications. Now on to the model performance results. The model produced highly encouraging results and demonstrated strong predictive performance. The overall accuracy reached 88.1%, meaning the model correctly classified nearly 9 out of every 10 transcripts. Sensitivity was 86.8%, indicating the model successfully identified most Alzheimer's cases. Specificity reaches 89.2%, demonstrating strong performance in recognizing healthy individuals and minimizing false positives. The model also achieved an area under the curve, or AUC score, of 0.934. In machine learning, an AUC above 0.9 is generally considered excellent and indicates strong separation between classes. Feature importance analysis revealed that lexical diversity was the strongest predictor of cognitive impairment, followed closely by the VLI. These findings suggest that language patterns contain substantial information about cognitive health and can be effectively analyzed by AI systems. The impact of cognitive screening. This research demonstrates how AI-powered speech analysis could become a practical and scalable tool for cognitive screening. Imagine a future in which a person speaks into a smartphone for a few minutes and receives a preliminary cognitive assessment. Such systems could be integrated into telehealth platforms, primary care clinics, and remote monitoring programs. Because speech collection is fast, non-invasive, and inexpensive, it has the potential to reach populations that may not have access to specialized neurological testing. Ultimately, the long-term vision is to create accessible AI systems capable of identifying cognitive decline earlier, supporting clinicians in decision-making, and improving patient outcomes worldwide. Thank you for your time, and I owe this all to YRI Fellowship for helping me get to this point. Thank you for listening to my presentation.